this wonderful workshop and also for giving me the opportunity to talk about this work. I'm not going to talk about NLC, so you might be disappointed, or any doped Hubbard model, but I will talk about the Hubbard model in one dimension. So let me start by quantum gas microscopes, and people here are not strangers to quantum gas microscopy. We've realized that this is a prominent tool to study strongly correlated electronic systems or strongly correlated systems. In general, we've heard about new attractive Hubbard measurements, also triangular lattice. And these are, of course, projective measurements that we can use to calculate all sorts of spin and charge correlation functions by simply counting what's going on in these pictures. They are considered diagonal observables because they are basically density and connected to the diagonal elements of your Green's function. So there is a question here, and that is whether or not the fact that currently these measurements don't access the off-diagonal elements of the Green's function are going to affect the insight that we can get from these snapshots at exotic, interesting, low-temperature behaviors. So this talk is about that, about some insights maybe into these off-diagonal elements from these diagonal measurements. So we can, of course, look at them and analyze these by hand doing these countings, but you can also show them to machines and ask them to detect various interesting correlation functions or phase changes for you, within these snapshots, within these diagonal measurements. And this was really pioneered by Annavold in 2019. And later, people started coming up with more sophisticated machines like correlated convolutional neural networks here, where you basically built in all possible correlations that you can have into your neural network, and at the end, the neural network can tell you which one of them is dominant in these snapshots. And later, similar ideas were used to find patterns that were consistent with particular phases in the programmable quantum simulators using Rydberg atoms. So we've done similar work back in 2019 in collaboration with Wasim and his group. We also studied these snapshots using machines. And our idea was really simple. We showed the neural network's snapshots at two extreme temperatures. In this case, initially, the snapshots were coming from the doping of 18% around this strange metal phase in the 2D, in the Cooper phase diagram. And we just simply ask the machine to distinguish snapshots that are taken at high temperatures from those that are taken at low temperatures. Now, if you believe that at high temperatures everything is random and there's no really interesting patterns in your snapshots, you might be convinced that if you have a convolutional neural network, then the filters in your convolutional neural network that are directly in touch with the snapshots and convolve with them will pick up interesting patterns that might have appeared at low temperatures in your snapshots. So simply by doing this training and then looking at the filters, we thought we can look for interesting physics. And there were some benchmarkings at the beginning. I should say that there were at the time two types of snapshots that they could take in Wasim's group, and One of them was obviously single species snapshots, and the other one was local moments. You can also think of them as density minus double-ons. So we did our work with both of these types of snapshots. So this gives you an unbiased way to discover patterns and physics in them. And so here you can see that if I do this process with single species snapshots near half filling, my filter is going to pick up this checkerboard structure, which is obviously an indicator for the antiferromagnetic correlations that are building up at low temperatures. These are different runs, and you can see that this pattern shows up in different ways, but it's pretty long range within the filter that you have if you're near half filling. If you go away from half filling at this 18% doping, you see shorter range, but still antiferromagnetic correlations. So you can do the same thing with snapshots of local moments. And here, near half filling, we were able to recover these types of double-on hole fluctuations in our filters, and they showed up as 2 white pixels, which we know is going to be the case with these single snapshots, snapshots that don't have double occupancies in them. So yeah, so this is the type of fluctuations that was discovered earlier, and they also show up in these filters. If you go away from half filling with these local moment snapshots, things become a bit messy, and at least to the naked eye, there is nothing immediately discernible from the filters. However, you can make it a bit more complicated, make your network bigger, or increase the number of filters in your neural network, and at some point you realize that the network becomes sensitive, smart enough to become sensitive to whatever is happening in the strange metal phase at low temperatures, and the whole network can at that point act like a measure, or the output of the whole network can act like a measure for this strange metallicity around 18% or 20% doping, and kind of go down as you go away from that doping. So I'm not really.
So how do you know it's indicating strange metallicity and not something else at that density?
Yeah. So when I say strange metallicity, I should say whatever is happening at that doping. So yeah,
okay.
it could be static correlations in your local moments. But yeah, of course, strange metal phase is a dynamic phase, and one has to be careful.
So yeah. What did it pick up? What's the y-axis?
The y-axis is, so these are when you train your neural network using these spin up or spin down snapshots, so one species only, that's where you pick up magnetic correlations in your filters. This one uses snapshots of local moments, basically density minus double occupancies, and you pick up things like this.
Right. So that y-axis is the.
Oh, here?
Yeah.
Oh, I'm sorry. Yeah. So I'm not really. So what I wanted to say next is that I'm not really going to talk about this. This is a whole different talk that I've given, and I've gotten tired of it. So I figured I should switch to something new. But this is some measure. This is basically output of your neural network. The output at the cold neuron of your neural network. However, you have to be careful here because density is itself a very straightforward indicator for the neural network so the training happens here at 18% doping, and when you go away from half filling, you can say the network can just look at the density and figure out that you're away from that filling and give you something like this. So this delta here is when you subtract that effect, effectively subtract that effect from the output of your neural network. So this is pure correlation, so whatever is happening.
so sorry to be confused, but like the double on hole fluctuations should occur near half filling, and I'm so confused by the
Yeah.
x-axis showing something strong at 80% filling.
That's what I'm confused about.
Yeah, so this is not related to this. These
Okay.
are, yeah,
I'm just correcting
right.
that. Okay.
Yeah, so just like
The wrong
these are
place.
different trainings at different densities, and even like each of these panels is a different run of its own. Here, this is what happens at half filling, and then this is something that you can pull out of your neural network, a measure for this, whatever is happening at low temperatures at that density. So I guess so the motivation here was that there is no order parameter for this strange metal phase, and we have these diagonal projected measurements. Can we say something about that strange metal phase? So the motivation for this talk is also kind of the same thing, but within a different model. In the 1D version of the Hubbard model and the extended version. And this is going to be all theory. So here is the outline. I'm going to talk about this extended Fermi-Hubbard model in 1D. And by extended, I don't mean T prime. I mean repulsive V, which is the near neighbor interaction. And then I'll briefly introduce the method that we use to simulate it. We want to emulate these snapshots that exist from that come from the quantum gas microscope. So I'll tell you a little bit about sampling the matrix product state to get those emulated snapshots, and then I analyze them using two different methods. So PCA, you might be familiar with this already, but this one is a relatively new measure, which is going to be the focus of the second half. Yeah, so this is the Hubbard model. Everybody is familiar with everything here. This is the nearest neighbor repulsion. And this is a phase diagram, kind of state of the art for this model. Of course, you can imagine that people have done a ton of DMRG or variations of DMRG for this model, and so you can see this is U and V, the two interactions I have. An infinitesimal U creates this SDW phase, and on the other hand, if I don't have any U and a very small V, also induces charge density order, and you can see their classical depictions here. But what is probably much less known is that in a narrow region between these two phases, at small u, u less than about 10, you get an off-diagonal order, which is a bond order. It's called bond order wave, BOW, and it's basically strong weak kinetic energy on alternating bonds. And there are, of course, two phase transitions here. As you go sit at a particular U and you increase your V, this phase transition is a continuous transition. This other one from BOW to CDW is also a continuous transition up to some U, and then the character changes to a first order transition, and then you have a terminal point here where you have a direct transition from SCW to BOW. So what we want to do is to simulate this using the best method that we have access to, create snapshots, and then analyze those snapshots for finding, again, in some unbiased way, finding these two transitions just by looking at these diagonal projected measurements. So I can't really say much about the method because I'm not a DMRG expert or even a DMRG person. But this is based on DMRG. It's called variational uniform MPS, matrix product state. It's translationally invariant. It directly works in the thermodynamic limit. And it's basically like what Philip said earlier. You have a unit cell, and you just repeat the same unit cell to get the thermodynamic limit. This is two different methods were combined to create this, and you can Matt Fishman, who was one of our collaborators, was also involved in that development of this method. And it's apparently efficient for this type of models where you have long-range interactions in your model. So here, because we have this type of these types of orders, we 2 unit cell, our unit cell is going to be 2-site unit cell. That's what we're going to choose as our unit cell in this MPS. So these are results directly from this Rumps technique. And now you can imagine that you have, in your unit cell, you have 2 sites and you have 2 bonds. And you can measure the energy on each of those bonds. So that's what I'm showing here for 2 different values of U. So this is U equal 5. And you can see that in the SDW. So here I'm going from SDW up, crossing these boundaries and going to CDW. And in SDW, you don't have any breaking of the translational symmetry. So these 2 are perfectly equal to each other. And as soon as you enter this BOW phase, these start to deviate from each other, which makes sense because that's basically the order parameter for you for that state. And then there is also a growing difference as you go to the CDW phase. What's interesting is that if you look at these carefully, you see that the transition from BOW to CDW is kind of smooth in terms of these energies here, compared to here. When used larger, it kind of becomes first order. So the nature of this transition is also kind of captured in these plots. You can look at the entanglement entropy by partitioning your chain in 2 different ways. Again, breaking the 2 different bonds that you have in your unit cell. And you can imagine that, again, as you enter your bond ordered wave phase, these are going to bifurcate. But then in the SDW and CDW, they are all the same because you have the same bonds in those 2 phases. So these are directly from from bumps to kind of benchmark that these numbers are consistent with each other between the energy and entanglement entropy, and also with previous results from other groups. So I'm going to tell you about sampling a little bit. Again, this is not really. This was the work by two of the collaborators. So I'll just mention quickly that to sample, we want to do that on finite systems. So you take your unit cell and you basically repeat that tensor that represents your tensors that represent your unit cell as many times as you want. In this case, we wanted to have 32-site system, so we had to repeat this unit cell 16 times. And you proceed with sampling this MPS just like you sample any other MPS. So we generated, so for each value, so we do different cuts as you saw for fixed value of U and multiple values of V. And for every one of those values of U and V, we have 50,000 of these samples. And the way you organize them is shown here. These are going to be obviously bit strings, and you have 2 bits for every site. These arrows show what each box corresponds to, and then the blue shading means that at site number 1 you actually have a spin down. At this site you have spin up, and so on. So this is going to be 2L, which means in this case it's going to be a 64 bit string. Okay. So I have to talk about symmetry breaking that happens for SU2. You break the SU2 symmetry in bumps. So we don't want that to affect the results. We don't want that to bias our samples. So we have to fix that, and we do that by locally rotating the spin at every site, and then uniformly repeating that at all sites. So that happens before every sampling. So for every sample, you have this direction, you have this spin direction in a random direction. Also, if you are in the BOW or CDW phase, the Z2 symmetry is obviously broken, and that is actually essential for our analysis. We don't want to sample from the two degenerate ground state with equal probability. We actually want that to be broken to sample from one of the two Z2 symmetry wave functions, ground state. And so you might say, okay, so this is your biasing, your calculations, but this is, remember, this is related to what happens in quantum gas microscopes and in experiments. And this is easily possible to do also in cold atoms by a combination of having open boundary conditions and an even number of sites. These boundary conditions are basically pinning fields for your bonds, for the strength of your bonds. And so you can see in this simulation the diagonalization of small chains, that if you have an even number of sites, which are these zigzag lines, the bonds, so this is the bond energy of the bond, and you can see that at the boundaries you have the strong bonds. So you can kind of pin your bonds at the boundary, which would be in the broken symmetry regime. So we're going to do that. We're going to sample from one of these two degenerate states and use that without loss of generality when it comes to comparing with what could happen in the experiments. This is one of the two methods that I mentioned, and if you're not familiar with PCA, it's a simple linear technique that you can apply to your data. This X is what we call matrix of data, so you take all these bit strings and you put them in a big matrix as rows of a big matrix X. You calculate the covariance matrix, and you find the eigenvalues and eigenvectors of that matrix. What essentially this does is that your the eigenvector corresponding to the largest eigenvalue is going to tell you the linear combination that you can form with your original data to get the largest variance in your data. So the most important linear feature, will be encoded in the eigenvector corresponding to the largest eigenvalue of the covariance matrix. So what I'm plotting here as these blue dots is the weighted eigenvalues of this covariance matrix, and you can see that there is a large eigenvalue, then everything kind of goes down. What we realized was that if we, instead of taking these 64-bit bit strings and running them through PCA, if we instead first concatenate multiple of them and create larger bit strings, then things become much sharper, much more improved when it comes to PCA, picking up the differences between them in different phases. So this red, these set of red points that you see here, these are PCA results. These are the weighted eigenvalues after concatenating 200 of these samples together before running them through PCA. So in that case, you get a really large first eigenvalue, and pretty much everything else is close to zero, telling you that there is one important feature that the PCA is picking up, and everything else is not important as far as this linear method is concerned. So you use that eigenvector corresponding to the first eigenvalue and also the second eigenvalue just for visualization purposes, and you project your data onto those eigenvectors. And so the plots that you see here are those projections. This is the first principal component, and this is the second principal component. Nothing really changes significantly as you go up, but if you look at the results after concatenation, you see that there are two very clear clusters that show up in your projective space or in your low-dimensional space. And if you do this carefully, you realize that all these points are the CDW snapshots, and everything else, the BOW and SDW snapshots, they all fall into this cluster. If you look at the eigenvector corresponding to the largest eigenvalue itself, you realize that this is the pi component of the Fourier transform of density. So it perfectly captures the order parameter for CDW. It can really tell where the CDW phase transition is happening, but not much about the BOW to SDW to BOW phase. This is more clear if you plot, if you come here and you, for every value of B, for every color here, average everything in this direction and plot them as a function of V, you see that this first principal component really shows a sharp increase as you enter the CDW phase, but there's no signature from the first or the second principal component for this first phase transition. When you have a large U and you have a first order transition, that also shows up in this first principal component. You go from something smooth to something sharp. Okay, so this is a linear method. This is really the very basic thing you can do with any big data you have. Now let me tell you about something different, which is called multi-scale structural complexity. In the last few minutes I have. This was proposed recently, and the authors of this paper actually used this picture of zebras to explain how this is computed. So very quickly, you partition this image into lambda by lambda sections, and in the very first step, you just take the average of the pixels within every box here, and you create another map, another image of those averages. You do that for every one of them. You get something that is much smaller, but then you, in the second step, you repeat this value 4 times in this case to get, well, not exactly 4 times, but you just increase the size of this region so that the number of pixels in this case is the same as the original picture, right? So it's just a repeating of these averages. And then in the last step, you calculate the inner product of this image, of this rescaled or coarse-grained image, and the original image. That overlap gives you one number, and then you go ahead and repeat this process several times. In the next step, you would take 4 of these big pixels and you average them, and then you repeat the process until there is nothing to average anymore. And if you add up all those numbers from all these different steps, that's the structural complexity measure. So really simple, something you can implement in in a few lines in your Python code, maybe less than 10 lines. And see, these are some other interesting calculations that they have done in this paper, showing, I'll probably have to skip this, that this is a food dye in water dissolving, and it's the most complex in this stage, in the middle stage, where the thing is actually dissolving and you have water and dye, a mixture, and then it's really small in these two boring regions at the either end. It's really the only formula you need, and it's just overlaps. I wanted this as a fun exercise for everyone to tell me if I do the similar partitioning that you saw for zebras, which one of them has the largest complexity. So I was torn between C and F. So you could probably tell by I. It caught me by surprise a little bit because it is actually F in that scale that I showed you earlier. This is complex. If you, I guess, zoom in a little bit more, maybe this one would be more complex. But yeah, it's really fun to play with this. So back to our bit strings, we do the same. They have another paper, the follow-up paper, in which they actually showed how to do this for bit strings. So we follow their recipe, and it starts with concatenation, and you go through this process now. Our lambda here is 4 bits because you want to take 2 sites to do this. So you repeat this process many times, and then you plot that as a function. Plot this complexity complexity measure as a function of b. We do one other thing, and that is we translate our bit strings by 1 site and repeat the same process. When you do that, you change the number of strong bonds, it turns out, in your bit strings if you're in the BOW phase, and that can affect the behavior of this complexity measure in the BOW phase. So in the interest of time, let me just...
So you go from zeros and ones to basically rational numbers, right? In your intermediates?
Yes. Yeah, you do. So yeah, so these are the results. This is the original one, and this is after doing this shifting, and you can see clearly that this thing bifurcates again in the BOW phase, and more or less in the CDW and SDW phases, they are on top of each other. Very closely, this follows the entanglement entropy measure and predicts these phase boundaries pretty accurately. These match the result from entanglement entropy very nicely. But remember, this is what we did all with snapshots. There's no fancy partitioning or anything like that going on. Even if you had access to only one of these, you would have a kink here, and then you would have some coming to another sharp feature here. So maybe you could still look at the boundaries. If you don't have a BOW phase, it just drops to another value. So this is the phase diagram. I don't really need to say much, except that again, it results from entanglement entropy and matches whatever you can get from the structural complexity very well. This idea of not mixing your samples from these 2 degenerate ground states is really important, and this really shows that importance, that if you do a sampling with equal mixture from these 2 ground states, you don't get any interesting behavior, at least not for this important first transition. But again, this is not really an issue if we want to connect that to experiments. So I'll just put this up, but I feel like this last point about potentially finding hidden things in snapshots kind of relates to what perhaps like Martin told us about attractive Hubbard and superfluid phase, which would be off diagonal, but might have some signatures in these density diagonal snapshots. Thank you so much. Sorry, I forgot to acknowledge I felt like this should have I thought the order was reversed. But yeah, these two guys at Flatiron really drove the calculations and the analysis. And Richard is also here. And Riz from NYU. My student Stephanie has kind of followed up on that, trying to do similar things with 2D snapshots. Thank you.
We have time for a few questions.
So in the last part, you chose your unit cell to be 2 sides, right? Because you kind of know that that's for the structural complexity stuff, right?
What did I choose?
Like you choose kind of your lambda or however you call it to be 2 physical sides.
Right.
Would
yeah.
this still have worked if you had chosen to be, I don't know, 4 sides or?
That's a good question. You just get, yeah, I think the signals might have not been as strong. So yeah, it is a balance between, you want to really choose the smallest lambda because you quickly exponentially increase the window of averaging and there's nothing else to do. So you want to choose the smallest lambda possible. I'm not sure if we tried anything larger, but I would think that things would be less interesting.
One question: is there any exact result that relates any observable you get from these processing algorithms to like real physical setup?
Yes, you can. It's not complicated. You can. Let's see. So you can look at what's happening. Maybe this would be even better. Yeah. So when you do this averaging, this is a simple average of densities, right? And then when you do the inner product of these 2 bit strings, it's some average times the original stuff. So you can imagine these are density correlations, or a mix of density or spin correlations. You're just calculating correlation functions by doing these inner products, but these are long range correlations. So some weird mixture of, I think we worked out a few terms of what the exact correlation functions are, but they just become longer and longer range as you do more averaging. And these inner products, you just incorporate more and more of these long-range correlations. But these are really 2-point correlation functions. Nothing fancy.
Maybe in this connection. So you said at the end that there might be some hope to detect some hidden order with this. And so did you apply, or could you apply this to like an SPT phase kind of hidden order, where we know that there's some kind of order, but we know that it's hidden and it's not visible in 2-point correlation function? Would an algorithm be able to pick this up?
That's the hope. This is fresh out of the oven, well, almost. Just posted this on arXiv, and so we are thinking about other possible routes and models to try this on. But I myself just really recently got introduced to this, so. No, we haven't tried, but yeah, we would be interested.
How interpretable is this? Is there any way to figure out what kind of correlations actually give rise to these different measurements of your complexity?
Yeah, that's a good question. Yeah, we haven't really done that, but yeah, you could basically go ahead and look under the hood for these values and see what is contributing to them the most.
Yeah.
Which one of these correlation functions? Yeah, that's a good question. Yeah.
So it seems that it's really important to do this shifting to resolve these 2 branches. But in this case, this BOW phase, it's this 2-side bond essentially. So if we were to try to resolve something that has, I don't know, more like a plaquette structure or something like that,
Yeah.
should one try like, I don't know, shifting like diagonally or other types of things, and then at one point you should find that, I don't know, at least for this BOW, if you shift two times,
Right.
I think you should recover one of the curves, right?
Right.
Okay.
Shift one lattice or 2 of these bits. Yeah. I mean, that's a great point. You have to, in this case, we knew the physics, so we could do this, processing. But yeah, I think if you can use some insight from physics, that would be really helpful. Yeah, it is important. It is important to maybe try different things, right? Try different shiftings or different unit cells or different types of samplings to do this. But yeah.
So no more questions. Let's thank Ehsan and all the speakers again. And I leave the ground to Marcus.